No.
Welcome everybody to the online seminar series, Machine Learning Needs Mathematical Optimization. We have today the great pleasure of having Jacek Gondzio, who is a full professor at the School of Mathematics of the University of Edinburgh. His main research interests are large-scale optimization, sparse matrix methods in optimization, and parallel computing techniques in optimization. So if you go to the website of Jacek, you will see that he talks about solving a problem with 2 to the power 40, so a trillion data points in 2015. So clearly we are talking about large-scale optimization already at that time. So his research has appeared in prestigious outlets such as European Journal of Operational Research, Mathematical Programming, Operations Research, and Science Journal on Optimization. He has been very successful in raising funding from the EPSRC, Google Research, to name a few. And in 2019, the Europe Working Group on Optimization made him an Europe Fellow. To end, he has ample editorial service. He's currently a member of the editorial board of Computational Optimization and Applications, European Journal of Operational Research, Mathematical Programming Computation, and Optimization Methods and Software. So, Jacek, we are very, very, very pleased having you here today. And the floor is yours. For the audience, we will do as usual. If you have very urgent questions, please put them in the chat. Otherwise, we will have time for a Q&A session at the end of Jacek's talk. Thank you so much.
Thank you very much, Dolores, for your nice introduction. Thanks, everybody who decided to spend 1 hour of their afternoon time or morning time if you are on the other continent. To spend and to listen about interior point methods again. So yeah, my pleasure to entertain you in the coming 1 hour or so. Can everybody hear me well? Right. So
we can hear you well, yes.
Perfect. Thank you very much. I'd like to talk today about various applications of interior point methods that run through sparse approximations up to certain examples of discrete optimal transport, both on dense graphs or on sparse graphs. This will be the subject of my talk. Here's the motivation. Sparsity, understood as the presence of only a few non-zero entries in the solution vector, is often a sought feature in some optimization applications, in particular in applications from machine learning or computational statistics. And it is common to use first-order methods for such problems, but I would like to make a gentle point that sometimes using the second-order methods may be advantageous. It certainly is more stable and more reliable. Where these sparse approximations appear? They appear in statistics or in machine learning, for example, the classification, support vector machines, in inverse problems where we would like to pick up as few features which are non-zero, which are relevant as possible. And then in image processing and signal processing. But for an optimizer, this is just solving such an example optimization problem in which the objective is to minimize certain function, usually convex, but sometimes also includes the cases of non-convex functions f, where we would like the argument x to satisfy certain linear constraints, but additionally from this argument x, we would like it to be sparse. And the good tool to reveal sparsity is to add norm1 to the objective function, because norm1 promotes the shape of the vector x such that most of its entries are 0, only the necessary ones are non-zero. This sparsity can be in the original space x, maybe in some other space, like for example, in when total variation is used, this may be a different dictionary in which sparsity is desired. And there are, of course, plenty of methods, highly specialized first-order methods, which originate from the works of Yuri Nesterovich, Stephen Wright, and many other authors. If we try to think about first-order methods and second-order methods, then, well, I frequently hear people giving talks about them, and they start the talk by saying, oh, don't even think of using second-order information, it's too expensive. And I think this is an unfounded criticism, and it is usually based on some sort of unfair comparison, which uses specialized first-order methods and opposes them to the very general, off-the-shelf second-order methods. A fair comparison would be to specialize the second-order methods and then compare them with the specialized first-order ones. So that's what I'd like to demonstrate today. This L1 regularization, if you consider something simple like least squares problems, which has an extra term to promote sparsity in vector x, may be viewed as rather an easy optimization problem. We just want to solve least squares problems with some extra requirement in it. There are no constraints, and unconstrained optimization is also an element considered to be easy. But there is a little bit of an issue. This is the non-differentiability of norm 1. And there are many ways of treating non-differentiability, but two of them are listed here. One is replace absolute value of x with the difference of, with the sum of positive and negative part of the vector. So first of all, split the vector into positive and negative part of it, and then write the absolute value of x as a sum of u plus b. Or another possibility is to use some sort of smoothing, some function which would replace the absolute value and make it differentiable close to 0. This is an example, the pseudo-Huber function, which approximates pretty well the blue line. The blue line is the true absolute value. The green line is this pseudo-Huber function. And as you can see, I hope you can see the digits here. These are very small numbers, so this is already zoomed very close to 0. But in such case, if we do such replacements, we will need some sort of homotopy, some sort of a mathematical tool to replace a difficult problem with a sequence of problems that are supposedly easier to solve. And these could be, if we use this splitting into positive and negative part, then we will have inequalities to deal with, and there is nothing better for inequalities than interior point methods, as I hope to convince you. And if we use pseudo-Huber regression, then we will use some other form of continuation. Well, having these goals raises immediately pretty obvious questions. How are we going to do it? Is there a theory that would back it up? And will it work in practice? So there is a positive answer to these questions. First of all, we will use an approximate Hessian. So we are not going to use complete second-order information, but just a little bit of it, just to throw a little bit more stability into the algorithms. And this means that we may use Inexact Newton method, which is a very well-established tool for solving non-linear equations or for solving non-linear optimization problems. And it has also been demonstrated to be useful in the context of interior point method by Stefania Belladia. Inexact Newton method means that rather than struggling to solve this Newton equation to perfect accuracy, we are prepared to accept certain error in the equation, and as long as this error, r, is bounded by a fraction of the right-hand side, then we will consider that this inexact Newton direction should still contain all the necessary information to allow the algorithm to progress quickly. And then we can use the continuation, either using Newton Conjugate Gradient, because allowing an error here opens the possibility to use iterative methods, as opposed to computing factorizations of the Hessian matrix. Or we can use interior point methods within inexact directions. If we think of using interior point method, then the question arises, will the use of inexact Newton directions compromise the behavior of interior point methods? It turns out that no, not at all. Surprisingly, even quite substantial error in the direction does not affect the complexity, the worst case complexity of interior point method. Up to 30% error is allowed, and still the so-called short step method converges in O of square root of n iterations. So there is no degradation of worst case complexity result. And if we use a more practical interior point method, the one that relies on symmetric neighborhood, then we need to be a little bit more careful, but still up to 5% error in the direction does not degrade the complexity result. So these are good news, that from theoretical point of view, interior point method can work with inexact directions. Also, this other example, when norm 1 is replaced with a pseudo-Huber function, like here, like in the case of compressed sensing, we may observe that we will create a sequence of problems which, rather than solve the original problem, will substitute it and solve the sequence of such auxiliary problems, which will depend on the parameter μ, and parameter μ will gradually go to 0. Here, the theory states that although this is not a perfect function, norm 1, it is only a substitute, still the solution of this problem is not far away from the solution of the problem we are really interested in. Actually, the distance between the true solution we are after and the solution of our approximate problem is small and goes down as quickly as the square root of this parameter μ, which appears in the pseudo-Huber function. Again, this is backed up by theoretical developments. In the last 5 minutes or so, I'd like to give you a very, very quick overview of interior point methods, and then I'll move on to applications. So interior point methods are based on a surprising, I'm tempted to say shocking mathematical concept, because we deal with linear programming problem by adding a non-linear function to it. And this is very, very much going against the centuries of mathematics where the opposite was done. When the problem is non-linear and difficult, we use local linearization to make it easier. Here, we have something to gain by adding a non-linear function to the objective. This non-linear function is the logarithmic barrier, a very particular function that can be conveniently used to replace inequalities and guide the optimization algorithm. Let me remind you the very basics of linear programming. This is the primal LP, the dual LP. They are connected with each other through the Lagrangian function, and the optimality conditions for these two problems can be stated as the set of equations satisfy primal feasibility, satisfy dual feasibility, satisfy the complementarity. Complementarity says that either the variable xj or the variable sj has to be 0 at optimality. And complementarity condition here will be written in a typical way for interior point community, that is using the diagonal matrices X and S, where on the diagonal of the matrix we place the entries of the vector X, here the entries of the vector S. So this capital X, capital S times E equal to 0 means nothing else but component-wise, every product Xj, Sj should be 0. Observe that this is a big difficulty, and in active set methods, this requires some kind of combinatorial commitment. We have to choose whether X will be 0 or S will be 0 to satisfy this equation. In interior point methods, we wouldn't have to do that because we replace linear programming problem with this barrier problem, which is now a non-linear optimization because the inequality X greater than or equal 0 has been replaced with logarithmic barrier. There is, of course, a Lagrangian, which can be written for this barrier problem. And now optimality conditions take a slightly different form because now the products Xj, Sj all have to be equal to the same value of the parameter mean, where this mean can be gradually taken down to 0. This is a major change in comparison with the previous form which forced 0 here, because now we do not have to make this decision, and we do not have to make the combinatorial guess whether x's will be 0 or s's will be 0 for a particular set of components. And this is the key thing which makes interior point methods so attractive. Also, there are profound mathematical reasons why the use of logarithmic barriers is such a good thing to do. First of all, logarithmic barrier is a self-concordant barrier, and this guarantees the polynomial complexity of the algorithm which relies on it. Also, it is a very mildly non-linear function, and because of that, Newton method applied to logarithmic barriers has a very wide region of where convergence is very good. So we can approximate this function, mildly nonlinear function, in a wide region around the point. And also this observation, which I have already made, that the use of logarithmic barrier guarantees that this difficult equation that we have to guess the solution of will be replaced with a much easier one, and gradually, by reducing the barrier parameter, yes, we will be approaching the same condition as here, but we will be doing it without necessarily committing ourselves to who is 0 out of these two variables. So the activity of the optimal solution will be only gradually revealed when the algorithm approaches optimal solution. There is a certain overarching feature of interior point methods that I'm not entirely sure people who do not use interior point methods entirely realize that. And I think it's the essential thing about IPMs is that the fact that all inequalities are always present in the objective through logarithmic barriers means that this method has a global view, has the overall view of the polytope at any point, and therefore is able to find the activity, find the essential subspace where the solution is hidden very, very quickly. In the rest of my talk, I'd like to focus on examples of sparse approximations. There are lots of such examples, and it wouldn't be possible to talk about all of them in a 1-hour talk. So I've selected those 3. The first one is our joint work with my very good Italian colleagues, Valentina De Simone, Daniela Di Serafino, who sadly passed away last year, my former PhD students, Spiros Ugapiotis and Marco Viola, and also discrete optimal transport problems. So this is the work with my PhD student, Filippo Zanetti, and also my postdoc, Stefano Cipolla. Let me start from sparse approximations and think about using interior point methods to solve them. In this paper, with Italian colleagues and Spiros, we decided to do the following exercise. We have taken 4 very well-known problems, and they are listed here. All of them have been solved using first-order methods, highly specialized first-order methods. We decided to take a general interior point code and specialize it to all these problems, and then compare to the dedicated first-order algorithms. So for sparse portfolio selection, we made a comparison with split-Bregman method. For classification models for functional magnetic resonance imaging, we will compare ourselves against FISTA and ADMM. For total variation-based Poisson image restoration, we made a comparison with prime or dual augmented Lagrangian method. And for linear classification, the machine learning problem, the regularized logistic regression, we will compare ourselves to new GLMNet and ADMM. So all these things are listed in the paper, but I will focus on this problem number 2. It wouldn't be possible to cover all these things in the talk. First of all, we will use the following modeling trick. We will take this problem, as written here, and transform it to such a formulation which is suitable for interior point method. So we need to replace norm1 here. We need to replace absolute value with the sum of positive and negative part of variable x, where positive is here the maximum of x0, negative is maximum of minus x and 0. Similarly, if we have another norm1, we will introduce a new variable to denote Lx. Lx will be equal to d, and d will be treated by the same trick, replaced by 2 twin brothers, the positive and negative part of d. Such a transformation makes the problem larger. To be precise, we double all the variables. Rather than 1x, we have now a copy x and its copy. Rather than Lx, we have the positive part of it and the negative part of it. So yes, the problem is larger, but the advantage is that it can be written in a standard form. It will have some inequalities, and we will be able to use interior point method to solve it. So yes, it's a larger problem, but it is a smooth problem. So second order method can be applied to it. And then we dealt with a binary classification of this functional magnetic resonance imaging data. This problem consists of solving some least squares in which the solution has to be sparse in its original space and additionally has to guarantee sparsity in this discrete anisotropic total variation, meaning that in all 3 dimensions we would like to have relatively few changes in the vector LV. There's a good mathematical justification, mathematical and engineering justification why such models are relevant for functional magnetic resonance imaging. Here, I'll give you the results of what happens when such problems are solved with 3 different algorithms: interior point, FISTA, and ADMM. And I know that tables and talks do not easily go, so here I just would like to pick up 1 row from this table, sorry, 3 rows of this table, which are perfectly comparable. This is the behavior of interior point method, the behavior of FISTA, and the behavior of ADMM. And we compare the following indicators: accuracy, to which optimization problem is solved, something called corrected pairwise overlap, which controls how well the voxels are selected, the stability of their selection, and finally sparsity, which here is understood as density. So whenever we talk about density, we would like the density to be as small as possible to achieve sparsity. In other words, ACC and corrected overlap, we'd like them to be as close to 100% as possible, while density, we would like to be as close to 0 as possible. And as you can see, when interior point method is used, it does deliver over 80% of accuracy, over 80% of corrected overlap, and 2.5 to 3% density. For phi-star, numbers are still reasonably good, but sparsity is more difficult for phi-star to be revealed. ADMM is completely in the woods. It is unable to find good corrected pairwise overlap. This should be close to 100%. Here it is just a fraction of a percent. On the other hand, the density, which we would like to be small, here is still very, very large, which means ADMM is very confused. It is unable to spot sparsity in the solution. The picture shown for you here shows the evolution of these parameters when time flies and the algorithm works on the optimization problem. What you might see here, the comparison is between interior point method and phi-star on the right. And what you can see is that interior point takes about 8 to 10 minutes to learn something about the problem and then quickly shoots to optimality. And once it shoots to optimality, about 17 minutes, the perfect minimum sparsity is determined, and also these parameters, the accuracy and the corrected overlap, reach its optimality and remain stable. This is not the case for phi-star. phi-star takes a lot of time to find the accurate solution and to find the right corrected overlap. But as far as sparsity is concerned, even after 30 minutes, it was impossible for phi-star to match the same sparsity as interior point. It would actually take 30 hours or maybe even more. It's a feature of first-order methods. They relatively quickly give you a rough solution, but if you would like to get higher, more accuracy in the solution, it will take a long time. I'm tempted to say it will take forever to get. Now let me move to the optimal transport. This is a class of optimization problems which go back 250 years to Gaspard Monge. But of course, we do know that they have attracted a lot of attention. For example, the Russian mathematician Leonid Kantorovich used them to solve transportation problems and was 30 years later awarded a Nobel Prize. But also we know that in the much more sophisticated mathematics, the pure maths part of the mathematical spectrum, optimal transport is very attractive in terms of transporting measures from one measure to another. And this led to Field's medal not long time ago. Optimal transport is, of course, described in many books. But what interests optimizers, what the interest of optimizers might be, is that its connection to network flow problems. Indeed, the discrete OP problem can be viewed as a network flow problem. Well, let me guide you a little bit through this optimal transport. We have two distributions of mass. The vector A in Rm describes the initial distribution of mass, and the vector B describes the desirable distribution of mass. And then we would like to transform mass in A into mass in B. And this can be written as through the set of linear equations and the set of feasible solutions which would make a decision where to move a particular element of mass from element I in vector A to element J in vector B. And then the optimal transport problem will be written as such a minimization where Cij is the unit cost of shipping mass from entry I in vector A to entry J in vector B. And Pij will be the amount of mass which is shipped there. Graphically, we can see that this discrete optimal transport consists of taking certain configuration, certain distribution of mass and transporting it to a new distribution. The red one needs to be transported and give us the shape of the blue one. Now, it is logical to expect that if we take a little piece of this red, we will bring it somewhere, but we do not know whether to this particular big part of the blue mass or maybe to another one. As you can see, this big concentration of mass from vector A will be distributed partly here and the part will go there. There is a bipartite graph which corresponds to the optimal solution. Bipartite meaning here we have the nodes corresponding to initial mass distribution, the nodes corresponding to the final mass distribution, and there is a connection indicating that yes, some mass will be shipped from there to there, and the width of the line indicates how much mass will be shipped. Here, for example, we have a very wide arc in the graph, which indicates a lot of this mass will be shipped to become a part of this big blue line here. Discrete optimal transport can be formulated as a linear programming problem, but then the LP constrained matrix will display some very particular structure. It will actually be a matrix which has m plus n constraints, where m and n are respectively dimensions of vectors a and b, and it will have a lot of n times n variables, because the variables indicate to all possible connections from m vector a to n vector b. By the way, the details of this are in the paper with Filippo Zanetti. So we are dealing with a very particular linear programming problem, the one that is very long. I could draw it like this. A problem that has significantly more columns than rows. Let me remind you, the number of columns is m times n, while the number of rows is just m plus n. Such problems are not new to optimization community. Optimization community solving lots of combinatorial problems would immediately recognize that this is a very nice structure to use column generation. And indeed, column generation replaces a long problem with the one which is much shorter, because it works with only a subset of columns of the original problem. So n bar here is a subset of all columns of the problem. And then this smaller linear programming problem, the restricted master problem, is much easier to solve. Graphically, we pick up a certain subset of columns from the long matrix. We solve this restricted master problem. Having solved it, we find out what the dual solution is, and we use the dual solution to decide which of the columns previously not taken into account are actually constructive, are actually attractive, and should be added to the problem. So these red ones are exactly, in my example, three most important of the missing columns that will be added, and the new restricted master problem will be solved. Column generation is a very well-known technique. It is usually applied in such a way that the problem is solved with the simplex method. But there are huge benefits of solving the problems using interior point method. First of all, we do not have to solve restricted master problem to optimality. And secondly, we will have dual variables which are incomparably richer in terms of information they contain. So they will allow us to much faster choose the missing columns, the ones that have to be appended to restricted master problem to deliver the solution of the original problem. But in terms of interior point, this means that we will use a specialization of the interior point method for such a problem that features long matrix A. We will use a kind of column generation type approach and work with a sparse solution set. That is, we will never update all variables x. The vector x may be extremely long, may go into billions of variables, and we'd like to update only a small subset of these variables. We will use simplex type pricing mechanism, which means that we will use some sort of oracle like in column generation. And also normal equations, the matrix that has to be inverted at each iteration of interior point method will be simplified, because rather than computing a complete form of it, we will only use outer products corresponding to a small subset of columns in set J, which is significantly smaller than the full subset from J equal 1 to n. When this matrix is built, we will use it either as a true approximation of normal equations, or we will use it to construct a preconditioner and then use the iterative method to solve normal equations. We tested this approach on discrete optimal transport benchmark collection, and these are images that have been perturbed, and then the optimal transport problem is to find the minimum of converting one image into another. So each of these images has 10 variations, and we solve actually 45 problems corresponding to transforming one image to another. The size of discrete optimal transport depends on the resolution of the problem. If the resolution is equal to R32, the number of constraints is 2R squared, but the number of variables is R power 4. So you can imagine it very quickly goes to large problems. For the resolution 256, we will already have 130,000 constraints in the problem and 4.3 billion variables. So this will already be the limit of what you can do on a desktop. If you'd like to go further, you would need a bigger machine. To be precise, a machine with more memory. This discrete optimal transport has been used by these authors, Schreiber, Schumacher, and Gottschlich, and they compared various codes for specialized codes for optimal transport. But to their surprise, and to our surprise, the code which turned out to be the most reliable and often the fastest was actually the network simplex method from Cplex. So, well, should we be surprised? Not really, because the discrete optimal transport problem is a network optimization problem for dense graph, and why shouldn't it be solved efficiently by the specialized network optimization solver like Cplex network simplex method? But what was interesting, what we've noticed when interior point was applied to it, is that when problems increase by a factor of 16, you see the red squares correspond to resolution 32, the blue to the resolution 64, and the green to the resolution 128. So a step from red to blue means we solve 16 times larger problem, but the solution time with interior point is something like 10 or 12 times larger. So that's a very good news. It means that interior point scales very well. The 16 times larger problem is solved not more than 16 times in the time which is not more than 16 times longer. The same cannot be said about Cplex. Cplex goes, by the way, this is a logarithmic scale now. The logarithmic scale for the dimension of the problem starts from 1 million, goes to 10 billion. And this is the solution time, starts from 0.1 second, 1 second, up to 10 power 4 seconds. And what you can see is that interior point scales sublinearly. By the way, linear here means that everything grows linearly with the dimension, while interior point goes a little bit sublinearly, simplex goes significantly faster than linearly, goes up in the solution time. What is also important is that neither simplex nor Lemon is a very highly specialized network optimizer, was able to solve the largest problem. For the largest problems, only interior point could deliver the solution. The other codes complained about not enough memory on the same computer. But by the way, I should mention that when I first showed these results to colleagues, I had a very good comment from Antonio Fragioni, who said, oh, you compare the interior point to simplex, you should compare it to Lemon, because Lemon is much faster than simplex. Indeed, it is significantly faster and better than simplex, and now we compare ourselves to Lemon, this code specialized network optimizer. The problems which you have seen so far from optimal transport corresponded to completely dense graphs in which we were looking for sparse solutions. And let me remind you, we were talking about images where the resolution R decided how many constraints we had and how many variables we had to deal with. And the problem was such that the number of constraints was significantly smaller than the number of columns. This is a feature for dense graphs. The incidence matrix is extremely long. But if we have sparse graphs, which means the possible connections from one vector to be transported to another vector, the possible connections are very limited, then we have sparse graphs on which we will also be looking for sparse solutions. So in this case, the shape of the linear programming problem is more typical, more like what we are used to in linear programming. That is, n is a few times larger, number of variables is a few times larger than the number of constraints, maybe 2, maybe 10 times larger. So we looked at what would happen in this case, and well, there is a connection between single commodity network flow. This is another perspective on this discrete optimal transport, because the LP matrix is in fact a graph node arc incidence matrix. But because of that, the normal equations matrix reveals the Laplacian structure. And Laplacian structure is very attractive because it guarantees that the matrix is diagonally dominant, and this allows us to use interior point information to significantly simplify this matrix. Once again, shorten the procedure to build the normal equations matrix and choose only a subset of columns, and either use this matrix as an approximation of normal equations or as a preconditioner for conjugate gradients to solve the system, to compute Newton directions. This is described in the new paper, which only 2 weeks ago was submitted for publication. A few examples how this works. So we have taken examples from suit sparse matrix collection and also some problems from the other public domain collections, but it's not easy to find graphs which are really large. That would be really challenging for these solvers. So here is the set of problems we were solving. They correspond to graphs which have between 1 million and 16 million nodes and up to 50 million edges. The graphs are really sparse. You see, the first one has on average six arcs per node. The other one has just 2 arcs, 2.1 edges per node. So these graphs are really very sparse. And it also means that the difficulty of optimal transport is elsewhere. The difficulty is in finding the right paths to ship the mass from the origin to destination. This graph demonstrates a comparison of the solution time between lemon and interior point method. The measure of time is logarithmic, so as you can see, for the smallest of problems, lemon is faster, is about 8 times faster than interior point. But whenever larger problems are dealt with, interior point is always faster. And the larger the problem is, the more significant is the saving delivered by interior point compared with lemon. And let me remind you once again, lemon is a highly sophisticated, for many years was considered to be unbeatable code for solving network optimization problems. So I think this brings me to conclusions of the talk, which are here on the last slide. I very much hope that I managed to convince you that there is an interest in using second-order methods, in particular interior point methods, to solve some of the sparse optimization problems. These interior point methods can rely on inexact Newton directions. Then they can use preconditioners for iterative methods, and they can work in a matrix-free regime, which is very attractive from the point of view of memory requirements. There is this important feature of interior point methods that they aggregate information about the whole problem, and thanks to that, they are able to quickly spot the activity, decide on the activity of optimal solution, what I call find the essential subspace where the solution is hidden. And when this is done, if it is properly exploited in the linear algebra, it really makes them very attractive tool to solve some large problems. So it works in interior points for LP or QP, it works in optimal transport, and it works in numerous applications of L1 regularization problems, these sparse approximation problems. Anybody is interested in using some of the tests and looking how really huge problems are solved, then I encourage you to have a look at our generators and our software. But for now, let me thank you for your attention, and I will be very happy to answer questions. Thank you.
Thank you very much, Jacek, for the very, very interesting presentation. So I open the floor for questions you may have for Jacek. And remember, raise your hand. Yeah, exactly. Raise your hand like Emmanuel, and then Jasone will give you the rights to the camera and to the video to ask the question yourself. Okay, so I guess Emmanuel is almost, yeah, has all the rights. Yeah.
I can control whether my camera is on, but this is not so important. Thank you, Jacek, for this great talk again. Another very pleasant to witness your progress. I have just one short question because I had difficulties understanding this. You showed us a double logarithmic diagram, right?
Say again, Manuel.
Logarithm horizontal axis, logarithm vertical axis. When comparing algorithms, I don't know. It must be around slide 30 or something. And you said something about linearity
yeah here.
This, yes, exactly.
So there is a logarithm of dimension of the problem and the logarithmic scale for measuring the solution time.
Thank you. So this means, to my limited understanding, it just means a polynomial dependence of time and size, right? Not a linear one. Is it correct?
Polynomial. Yes, you are right.
Okay, so then it would depend on the slope of these straight lines, how actually the behavior would be. It would not change anything about the relation. It's monotonic, of course, but the spread could be even more or less pronounced depending on the slope.
Yes, indeed.
Okay, thank you. Then I understood correctly. Thank you. And of course, my usual comments in all these lectures dealing with the L1 surrogate of measuring sparsity. If there's a chance to use the L0 norm, the exact sparsity measure, it would be nice. But I understand it is not so trivial to extend this to L0 norm because of missing properties of this.
Well, you are absolutely right. The L0, well, not norm, but the pseudo norm would be the right tool. But then the problem is inevitably combinatorial, which just makes it significantly more difficult to solve.
Well, there are continuous time variation formulations which are exact, but we probably should talk about this offline at some later.
Oh,
thank you.
Thank you.
Jacek, there is a question on the chat, and I have been asked to read it for you. Actually, it's two questions. So, what is the most expensive step forming the Newton normal equation, or solving it, one or the other? And the second question is the non-negativity relaxed?
Let me start from in bad order. The answer to the second question is very easy. No, the inequality is never relaxed. The inequality is monitored all the time, and it is forced to be maintained because of the use of logarithmic barrier function. And now let me go to the first question, which was about what the most expensive operation is. So in case of dense graphs, this operation, which requires computing outer products of all columns of the matrix A and then multiplying them with the appropriate theta j and adding together, is potentially an extremely expensive operation. Let me just remind you that this is done for the problem which is very, very long. It has n times n variables. So we have an extremely long matrix, and building normal equations, that is computing this sum, would be very expensive. Doing it for a small subset of columns is a huge saving. So this is the saving number one. Now, for certain problems, for sparse problems, building the full matrix is not so expensive, although building the full matrix will contribute more non-zero entries to the normal equations, and then they will become more difficult. The equations with them will become more difficult. So I would say for dense discrete optimal transport, this is the most expensive operation, and it's useful to replace it with something significantly cheaper. For sparse graphs, this operation is not so expensive, but the solution of the normal equations would then be quite expensive.
And I hope, Henry, that this answers your questions. Are there any other questions from the audience? I think there are no more questions, Jacek. So we have enjoyed very much your, again, very good presentation with dealing with large-scale optimization again, and talking about very current problems that we face in machine learning. And for the public, we hope to see you back next week when we are having another young session of the online seminar series. Thank you so much to all of you.
Thank you very much, everybody, for joining us today.